In this video, we will discuss free body diagrams. In kinetics problems, you relate the forces acting on an object to the acceleration caused by those forces using Newton's second law of motion. The sum of all forces acting on an object equals the object's mass times the acceleration of the object. It is critical that you account for all forces that affect the motion of the object significantly. A free body diagram is a tool that helps us identify those forces by isolating the object from its surroundings and replacing the surroundings with force vectors. Along with isolating the object and drawing force vectors, you also must draw coordinate axes and indicate the positive direction of the coordinates. Drawing a free body diagram is the first step in solving a kinetics problem, and it is crucial that you draw a correct free body diagram before attempting to solve the problem. It is worthwhile to spend a little extra time making sure that your free body diagram is correct because it will be the foundation for all the math that follows. An incorrect free body diagram usually will lead to an incorrect answer. Now we will look at 3 examples of how to draw a free body diagram using some of the forces that you will encounter in typical dynamics problems. In this first scenario, a ball that is attached to a spring is being pushed by someone's hand. Let's draw the free body diagram for the ball. First, we isolate the ball from its surroundings. Next, we draw the forces acting on the ball. Weight, which is the force due to gravity, is denoted by W or mg, where m is the mass of the object and g is the gravitational acceleration. The weight points downward toward the ground and acts at the center of mass. Next, the hand exerts a normal force on the ball. The normal force, which is usually denoted by N, always points toward the object. In this case, the normal force points away from the finger and toward the ball. The spring force acts at the surface of the object as well. This force may point toward or away from the object depending on whether the spring is in compression or tension. In this free body diagram, we have assumed that the spring is in compression and is pushing the ball. Finally, we draw a set of coordinate axes and denote the positive direction of each coordinate. We are now ready to start solving this kinetics problem. In this second scenario, a block is being pulled over a flat surface by a rope that is at an angle theta relative to the horizontal. To create the block's free body diagram, we first isolate the block from its surroundings. 4 forces act on this block. The block's weight acts downward. The normal force exerted by the ground acts upward. The rope is in tension and points away from the block's surface at an angle theta relative to the horizontal. And notice that ropes can only be in tension and never in compression. The final force is friction, which acts at the interface between the block and ground and opposes the sliding motion of the block. Finally, we draw a set of coordinate axes. In the third and final scenario, a ball sinks in a container of water. We isolate the ball and draw its free body diagram. The weight acts downward. The next force is drag, which is a form of friction that occurs when an object is moving at a different speed than the fluid in which it is immersed. The drag points in the direction of fluid motion as seen from the object's point of view. In this case, the ball is sinking in a stationary fluid. Since the fluid appears to move upward from the ball's point of view, drag points upward. If the ball were rising to the surface of the fluid, the drag would point downward. And if the ball were stationary, there would be no drag. In many dynamics problems, drag is relatively small compared to other forces acting on the object and can be ignored. Typically, drag is significant only when the object is traveling at high speeds. The final force acting on the object is the buoyant force, which points in the direction opposite of a hanging plumb bob. The buoyant force acts at the object's center of buoyancy. If the entire system is not accelerating, like in the picture shown here, the buoyant force points upward. The buoyant force is due to the pressure being higher on the bottom of an object compared to the top of the object. Buoyancy usually is significant when a solid object is immersed in a liquid, and usually will be small when a solid object is immersed in a gas like air. After drawing the coordinate axes, we are ready to solve this kinetics problem. The three scenarios in this video show some of the important forces that arise in kinetics problems. To review, drawing a free body diagram should be the first step when solving a kinetics problem. When drawing a free body diagram, isolate the body from its surroundings, identify and draw the significant forces acting on the isolated body, and draw the coordinate axes. One final comment about free body diagrams. When solving for an unknown force, sometimes it will not be clear which direction that force should be pointed in. In these cases, you can guess a direction. If the magnitude of the force ends up being positive, you have guessed correctly, and if the magnitude of the force is negative, you have guessed incorrectly and should rotate the force vector by 180 degrees.